Welcome back, everybody. The purpose of this video is to explain the use of variables, why we have them, what they do, how we can use them, how we can manipulate them, some interesting things about variables. So let's go ahead and get started. So beginning, let's talk about these three variable types right here. Specifically, these are three primitive types. All of these are, but let's just talk about the integer, the short, and the long. Now, 99.99% of the time, you could just use an integer and get away with it. It's going to be more than enough than what you need. But an integer is a 32-bit data structure, and it holds only whole numbers. Specifically, an integer, a short, and a long only hold whole numbers. You can't put a fraction in there. You can't put, 3.2 or 4.765, anything like that. You can only put whole numbers in these data structures. But even though they're limited in that sense, they're still very useful in that sense. So let's take a look at an integer. An integer has a range of negative 2.1 billion, roughly, to positive 2.1 billion. Now, there's also another data structure here called a uint, which is called an unsigned int. It has a range of 0 to about 4.2 billion. It just takes the negative out of it and puts it on the end towards the positive side. You won't need to use any of those in this class, but I figured I'd share it just to give you a little insight on kind of more data structures than what we're going to be talking about. So to demonstrate what I'm talking about with the whole negative 2.1 billion to 2 billion range thing, I'm going to show you what's called integer overflow. It's really kind of a cool thing that happens in computer science that you really have to think about, and I'll give some examples on why this is important. So I'm going to start by creating an integer. I'm just going to call it I. And then let's initialize it to 2 billion, or 2.1 billion. So 2 millions, thousands, hundreds. So this is a perfectly good value. My integer I is set. It says that it's signed but never used, but that'll eventually go away. And let's do something to it. So I want to change the value of I. I want to say I equals I plus, and remember, 2.1 billion is kind of the limit. It's actually, 2.147, yada, 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 some stuff. So let's add 300 million to this object. So 300,000 hundreds. Let's go ahead and print out the value of I right here, and then we'll print it out again. Oops. There we go. So, by just looking at this code, if you were to show this to your mom, if you were to show this to your grandma, or somebody who doesn't have a technical background, they would say, "Oh, well, 2.1 billion plus 300 million, that's going to be 2.4 million, right?" Wrong. Let's check this out. And remember, so Control F5. Whoa, what's going on here? How come we went backwards? We took 2.1 billion. That's the first thing we printed. When we add 300 million to it, we went to the other side. That's what happens with integers. That's what happens with any of these numeral data types. You get into a situation where if you overflow the maximum value of that data structure, it just flips around to the other side. And this comes down to a bunch of bit manipulation kind of stuff, which we're not going to get into deep with because it can get really complicated really quick. But I just want to demonstrate that this is the case. I had an algorithm one time that calculated the value of pi, and to do so, I had to constantly increase the value of an integer. And eventually my integer looped back around and it threw my data off, and I was like, wait a minute, what's going on? And I was super confused. Started doing some research into this, found this out. So instead of using an integer, I used a long, because a long has a much, much broader width of valid numbers. And this is a big number. For anyone who's not familiar with this kind of writing, so 9.2 times 10 to the 18. So what this is, and I'll write this down here, is, so 9.2 times 10 to the 18th is equal to 9.2, so I've moved over 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So imagine this, where we did have the decimal right here between the 9 and the 2. I moved it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 spots. So that's what this kind of dictates. So, this number compared to millions, thousands, hundreds. I mean, this is absurdly massive. A long is much, much, much bigger, or has a much, again, bigger width, a broader scope that it can't contain than a regular integer can. The downside to using longs just for everything, though, is that it's a 64-bit data structure. For every long you create, it's twice the size in terms of memory space as an integer. If I want to create a couple thousand of these, creating a couple thousand integers is going to be very manageable. A couple thousand longs, it's going to be twice the size. So it's going to start getting to a position where it's too much data that we want to get rid of. So similar to how a long is twice as big as an int when it comes to the amount of bits that it can hold, the range is definitely a lot more than 2 times because of exponential growth. A short is half as many bits as an integer. This is a very small range, but if you have, let's say, a huge data set of 1 million elements that you need to store in a database, if you knew those values were going to be between here, for example, let's say age, it's a person, you're trying to store a person in a database and they have an age. Nobody's living longer than this. I could promise you that. Maybe sometime in the future, but not anytime soon. Store their age as a short. It's going to make the overall million, data people that you have, their age value is going to be half the size as if you used an integer. So let's next talk about our next three data types, which can have decimal points after them. They can hold non-whole values. So very similar to what the int, the short, and the long was. We have the float, we have the double, and we have the decimal. The float's going to be the one you want to use most often. It has precision of 6 to 9 digits, which is fairly good. It's not bad, it's not good, but it's good enough for what you need. But it's also 32 bits. It's much smaller. Its range, and again, plus or minus here, because of the way the binary interactions work with floating point numbers, there is a plus or minus on the small end, and there's a plus or minus on the big end. This 3 right here makes it so we can't be as precise when it comes to the plus and minus. So this might be a little confusing. Just know that this is a relatively large range. This is a much, 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 much larger range. But when it comes to float and doubles, they're the same thing. One is just bigger than the other. A double is a little bit more precise. It can hold more values. It's also bigger. A decimal, on the other hand, if I was to store the value of pi somewhere, if I was going to store the value of pi in my computer, I would want to use a decimal. Now, a decimal can't get as big on the left-hand side of the decimal point. It can't get into the, huge numbers. It still can get pretty big. But what's powerful about a decimal is its precision after the decimal point is massive compared to a double or a float. 28 to 29 digits, you can guarantee precision. If I store pi in a value, it will do something. So let's go ahead and do another example here. So I'm just going to use my 3 variables up here. So remember, with a variable, I've declared it right here. It exists in the scope of my program, so I can use it. So if I come down here and I say my float equals 3.14, that's perfectly fine. It'll crash because I need to cast it to a float. Now this is something that's a little weird. Why am I putting an F in there? I'll explain that here in a minute. But something else we could do here is we could do math.pi, which I believe is a double. And because this is a double, I need to actually cast this to a float. Now, we'll get into casting when the class actually starts in the fall, but I'm converting this value down to a floating point number. And the way I'm doing that is simply by chopping off precision bits. That's basically what I'm doing. So let's go ahead and print my float. And then let's do the same thing with my double, but this time I don't want to cast it. So math.pi is hard-coded in the computer, in the language that we're using. as that value, 3.14159.265.35897931. But we're going to see an interesting thing. So let's go ahead and write this one out too. And let's see what happens. So check that out. So when I casted my float, or when I casted math.py to a float, I lost a bunch of precision. I got 3.141593. 1, 2, 3, 4, 5, 6. 6 digits of precision right here. So 6 to 9 digits. So we were close. We couldn't get all the way, but we got 6 digits. On the other hand, when we cast to a double, we get many, many, many more digits. So I've gone ahead and I've created a value for my decimal that is pi to 30 digits. And again, similar to how when I created that original float that was 3.14, I had to cast it with an F at the end of it. With the decimal, you have to put an M at the end of it. This is just an annoying thing that you have to do. It's kind of a specific to certain languages. C# definitely does this. But you get used to it pretty quick. I'm very much in the habit now of anytime I put something with a decimal point, I always put an F after it because I'm usually using a float. So now let's see what this prints out. So this is going to print out much, much more precision. So you might be wondering, why do they have a float? Why do they have a double? Why do they have a decimal? Why don't they just use, one or the other or whatever? The reason for this is, a floating point number is perfect for 99.9% of situations. Whereas, let's say we were in a scientific situation and we needed to be very, very precise. The value of pi, for example, that needs to be as close as possible to get the correct results. The computer scientists way back in the day decided we need multiple types of data types to represent very similar things instead of just all putting it into one, simply because of this fact. A decimal can be much more precise than a double or float can. So it's something that we have to consider as we go through this process. So that's it for the decimal types. Again, very useful. You'll find many uses for these. Let's talk about the more interesting types. So we have a character here, and let me pull up my internet browser real quick. Open this up, and I'm going to go to the ASCIItable.com. I think that's what it is. Yeah. So this is what a character is. A character can hold these values, specifically, 0, 1, 2, yada, 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 yada. But when you print it prints out whatever that character is. So I'm going to pull this back over to my other monitor, and let's go ahead and store something into my character. So I'm going to say my character, and I'm going to store something in there. Looking at our ASCII table here, let's store in P. Let's just store in P. So you notice here how I'm using apostrophes to put this, to indicate I want to do this. I want to store a character in it. If I was just to put P in here, it thinks P is a variable. It says P doesn't exist in a current context. By putting it within the apostrophes, it says, yes, this is a character. I want this to be a character. This is just like how I did, my string equals hello world. This is just like how I did that, except you use quotation marks with a string, you use apostrophes for a character. So something interesting to note is a string is technically an array of characters, or very similar to. They have some differences. When we get to arrays, I'll explain more of this, and as we get to string manipulation, we'll really dive into what to do with a string. But just know, a string is quite literally an array of characters. So let's say I do something like this. So I'm going to say that's my string right now with a space at the end. I want to say my string equals my string plus, and remember in our last video, this is called concatenation. I'm adding two strings together. If I put in a W in there, I just added W to this string. So let's continue doing this for WORLD. ORLD. Okay, so now let's see what happens. So right now I'm going to this, I'm going to print my string, just because I want to see what happens at first. So at first, I'm assuming my string equals hello, comma, space. So that's what should print out. Let's try it at the very end. So check that out. So I was able to append characters to the end of a string and print out the entire thing. So at this point in my code, so right here, my string, my string variable equals hello world, even though it's put together in this very, weird kind of way. After this right here is applied to my string variable, it sets it to equal hello world. So that's enough for strings. Let's start taking a look at booleans. So we have my bool up there, and I'm just going to set it to true, okay? I'm just going to say my bool equals true. Remember, a boolean data type holds either true or false. Something that's pretty well known in computer science is everything runs based off of a bit. A bit is either a 0 or a 1, an on or an off, a true or a false. A boolean represents that kind of structure. So let's just write that out and see what happens. True. So it's going to print out the actual value of that boolean at any given time. Now, the boolean data type is going to become very, very useful as we move forward once we get into our conditional statements unit, because it's what defines the conditional statement. If this is true, then do this. If this is true, do this. If this is not true, then do this. Things like that. So we'll get much deeper into booleans as we get there, but for now, we'll just leave it as a data type that holds true or false. So moving on to our reference types. And now the difference between our primitive types and our reference types is these are just set as values. Now a string is a little bit different in the sense a string is kind of both, but technically it's still a reference type. You can just set a string's value like we've done before. But an object, on the other hand, is kind of neat. An object is something that every single thing can be broken down to. So I have my object right here. I'm going to say my object equals my int. Now we have an error here because my int is unassigned. So I'm going to go ahead and assign it just right here. So I'm going to say my int equals 5. So I can store my integer into my object. There's a whole bunch of casting that goes on here, and it's kind of an inefficient operation. But it kind of demonstrates the fact that an object is everything. Everything can be broken down to an object. As the semester moves along and we get more into the situation where we're creating our, custom classes, a person class, an item class, inventory class, something like that. Every single one of those items or every single one of those classes can be broken down into an object. It's the base level. Everything inherits from object. So now that we've kind of explained what these are, let's kind of use them in a more interesting sense than what we've been doing so far. So let's start with integers. Now, let's say I want to do a simple mathematical operation. So I'm going to say my int equals 5, okay? And I want to say my int equals my int times 2. So what I'm doing is my int equals 5. Right here, this is literally the same as writing this. However, I want to use my variable because my variable changes over time. What if somewhere else in my code I was manipulating the value of my int and I wanted to use that actual value? That's what I want to use right here. So the expected value of this can be 10. So I'm going to console.writeLine my int. I'm going to run it, and we get exactly what we expected, 10. But now let's try something different. Now, you all are smart people. What is this? What is my int divided by 2? You're going to be saying, oh, it's 2.5, easy, look at me go. However, C# thinks it's a little different. C# thinks 5 divided by 2 is 2. You get those jokes in your math class and whatnot, 2 plus 2 equals 7 or whatever. That's basically what's happening in C#'s head. This doesn't make sense. Why is 5 divided by 2 2? And just to prove to you guys, I'm going to put 5 here. So 5 divided by 2. Let's go ahead and run this. It doesn't make any sense, right? Let's break it down even one further. Instead of putting my in here, we're just going to be 5 divided by 2. And remember, So this right here is a value. I can just straight up put this in my print statement. Your print statement doesn't always have to be something very specific. You could put almost anything in a console write line and it'll work. I'm going to run it again and we still get 2. This is so frustrating. I want 2.5. I want it to print 2.5. Oh my goodness. So check this out. If I simply cast both of these to floating point numbers, then we get what we're looking for. So as you go along the process, this isn't something you need to know right now, but as you start working more in code, start figuring it out, start learning more things, these kind of tricks are things that you'll learn pretty quickly. I kind of tripped up my my class at UCCS that I'm teaching by having them fix a bug that I implemented with a Celsius to Fahrenheit converter algorithm. I put, an equation like this, it was 5 divided by 9, but I didn't put the F on there or a D on there or an M on there to convert it to a decimal type variable. So they're sitting here trying to figure out why are they getting the wrong number, why are they getting the wrong number. It's literally because I just told the compiler to divide a whole number 5 by a whole number 2. It's going to give me the whole number version of what I asked for. So let's try doing something a little different here. I have my integer, it's called my int. Let's say I want to store pi in it. I'm going to put 3.14 in there. It's going to get mad at me because cannot implicitly convert type double to int. There's no nice way to do this. I could put an F here to try to convert it to a float. That's not going to work. An M to a decimal. That's not going to work. The only way to do this, and again, you don't need to know this, but I'm kind of demonstrating what's going on in the compiler's head right here. You can cast things by putting the data type in parentheses before it. So I just casted 3.14 to an integer. So great, red line goes away. Our problem is solved. We did it correctly. Wrong. What is this going to print out? Think about it. What in your head, what should this print out? I'll give you a hint. It's very similar to what we just did. So I'm going to run it, and we are going to get 3. So, it's an integer is an integer. You can't put a decimal type data, a value, in an integer. It can't be that way. An integer has to be a whole number. Same with a short and a long. So something else to note for variables is scope. Wherever you create the variable is where its scope is. So for example, let's say I have all of my types up here. I'm going to put 2 curly braces right here. I just created new scope. So if I, say my int equals 5, this is perfectly fine. So this integer, my int, exists within this curly brace and this curly brace. Therefore, you can see when I highlight them, I have selected this line of code right here that I wrote. But let's try this another way around. So I'm going to create an int, my other int, and I'm going to initialize it to 10. Cool. If I try to change it to 225, I can't. The scope of my int, again, is between this curly brace, the scope of my other int is between this curly brace and this curly brace. I can't actually get to it down here. It's not available for me. This is one of the biggest areas that I see beginner programmers really kind of mess up on. They get into a position where they're like, oh, but my variable's right here. Why can't I use it? Scope is a very big thing. The general way to kind of solve this is to go to your variable, go to the curly brace above it, and then go down. And keep in mind, when I say go to the variable, I don't just mean like go to the variable. I don't say, go to the variable and go to here. Go to where the variable is declared. Where it's declared is the type of memory that it lives in. So my int, this variable, starts right here. I initialize it right here. So it's going to exist between these 2 curly braces. And again, that's a very big thing to understand. If you ever run into an issue where, for example, the name my other int does not exist in the current context. Well, it's because it's in different curly braces. If I remove these curly braces, boom, everything works just fine, just as I would expect it to. So in a nutshell, data types are what you hold data in. Variables are what hold data types, which you hold data in. If you have a project and you need to remember something, let's say you need to take user input, enter a value 1 through 5. You need to take that input. You need to store that value somewhere so that you can use it. It's just like your brain. If somebody tells you something, You remember that so that you can recollect it later. As you go through classes, as you go through school, you're constantly fed information that you're supposed to recollect later. So that's basically the whole purpose of variables. And that's everything that we need to cover in terms of variables. So look forward to the next video, which is going to be covering conditional statements and Boolean expressions.